Welcome back to The Explainer. Today, we're diving into what I honestly think is the ultimate magic trick in artificial intelligence right now, surgically editing a neural network's brain. For years, we've basically been told that large language models are these impenetrable black boxes, right? That their knowledge is just this mysterious, swirling soup of billions of numbers. But what if I told you that researchers now have the tools to literally pause that system, decompile its brain into a structured database, and delete a single specific fact with absolute mathematical precision?
So let's jump right in with the premise that pretty much defies everything we've been taught about the smeared, distributed knowledge of LLMs. Conventional wisdom says that if you want a model to forget something, you have to undergo massive, incredibly expensive fine-tuning. But the lateral framework we're exploring today proves that you can isolate and completely remove a single fact, like Paris is the capital of France, without retraining a single byte of data.
Just look at this incredible before and after result from the Gemma 4 E2B model. When probed with the capital of France is, the original model cleanly outputs Paris. But after applying a microscopic mathematical patch, that exact output is completely absent. The fact has been entirely removed with absolutely zero bleed-through to the rest of the model's capabilities. To see how they actually pulled off this impossible feat, here is our roadmap for today. We'll be looking at deleting Paris from AI, decompiling the black box, querying the neural graph, the mathematical scalpel, and finally, cryptographic audit trails. Let's get into it. Section 1. Deleting Paris from AI. Now, the craziest part about this deletion is that it wasn't some massive brute force fine-tuning job. We didn't have to feed the model thousands of new examples to try and coerce it into forgetting. Instead, it was a single hyper-precise weight space edit made specifically to the gate_proj.weight matrix at layer 27 of the model. We're literally talking about a microscopic surgical intervention inside a massive matrix of numbers.
Section 2. Decompiling the black box. To edit a model, you first have to understand what's going on inside it. And instead of just treating these model weights as an opaque binary blob of unreadable math, the LARQL framework decompiles them into what's known as a vindex, or vector index. This fundamentally turns the AI model into a relational database. Imagine taking a giant, hopelessly tangled ball of yarn and perfectly organizing it into a neatly indexed filing cabinet. That is exactly what a vindex does for an AI.
So how does it do that? Well, by using a mathematical technique called singular value decomposition, or SVD, the vindex filters out all the noise. It isolates just the top 64 singular vectors of a layer, which, surprisingly, captures roughly 85% of the variance. By cutting away that noise, the vindex reveals exactly where the clean semantic concepts actually live. It maps out these entity associations and enables SQL-like queries. Plus, because it's essentially just a database now, you can browse an AI's brain entirely on a standard CPU. No expensive GPUs required at all.
Which brings us to Section 3, Querying the Neural Graph.
With our database metaphor established, how do we actually ask the model what it knows? Using LQL, that's the Lazarus query language, we can run actual code. For example, we can run a walk command for the prompt, the capital of France is, to trace exactly which features light up. When we run this, we aren't just getting text back. We're tracking the literal inference path through the neural graph, layer by layer, watching the concepts activate as the model thinks.
And here is the exact smoking gun that query uncovers. The trace leads us straight to feature 11.17.9 at layer 27. This single feature completely dominates the response with a massive gate score of 18.10. And look at the top tokens associated with it. We see capital in English, capitale in French, and Hauptstadt in German. This absolutely proves feature locality. The model's multilingual concept of a capital city isn't smeared everywhere across the network. It is cleanly and perfectly isolated right here in feature 11.17.9.
Okay, Section 4, the mathematical scalpel.
Now that we've found it, how do we extract it? We have to look at the universal four-stage circuit that researchers have mapped inside these models: broadcast, domain, entity commitment, and prediction. Because we understand this circuit, we know exactly where to intervene. We target Gate 3, the entity commitment zone. This is the precise depth in the network, usually about halfway through the layers, where the model locks in its semantic choice. It's the exact moment the model decides, yep, I am definitely talking about Paris.
And this is a massive paradigm shift, guys. Think about traditional fine-tuning versus a LARQL patch.
Fine-tuning is basically blunt force. You flood the model with new data, hoping it shifts the weights in the right direction. It's incredibly wasteful and notoriously unpredictable. A LARQL patch, on the other hand, is a surgical scalpel. It is an exact, deterministic mathematical update, a rank 1 projection that simply subtracts that specific feature's direction right out of the matrix. The rest of the model remains completely bit identical.
And because this edit is so surgically precise, the entire transaction can be represented by a remarkably tiny file. We're talking about a JSON receipt of just 100 bytes, which generates a patch file that is only 9 kilobytes in size. So instead of retraining gigabytes of data on a cluster of massive supercomputers, you're just supplying a tiny, instantly reversible file overlay that sidesteps the deleted fact at runtime.
Now you might be wondering, doesn't deleting Paris as a capital break the rest of the model's geography skills? The precision here is just staggering. If we ask the patch model about the capital of South Korea, it answers perfectly. If we ask what France is famous for, like wine and fashion, it answers perfectly. The Korean language capital fact relies on the exact same vocabulary feature we identified earlier, but it points in a slightly different mathematical direction, so it remains completely untouched. We strictly deleted Paris as a capital, and absolutely nothing else.
Let's step back and look at Section 5, Cryptographic Audit Trails. Being able to surgically edit a model like this isn't just a neat parlor trick. It's a real game changer for massive real-world legal and compliance headaches. Because the LARQL patch is an exact mathematical file, it leaves a perfect SHA-256 checksum, meaning you get a fully auditable cryptographic trail. We can finally enforce GDPR right-to-be-forgotten mandates or execute surgical copyright takedowns with absolute, undeniable proof that the data was removed. Plus, if a model outputs a hallucination, we can use the Vindex to forensically trace exactly which layer and feature introduced the error, and just patch it out before it happens again.
This fundamentally demystifies the black box. For years, deploying an AI meant crossing your fingers and hoping the model wouldn't misbehave based on some hidden, smeared training data. But by turning the model into a queryable graph, researchers have proven that a major structural crisis in digital architecture has a definitive solution. AI weights are no longer uneditable math. They can be surgically altered with exact deterministic control.
The implications here are honestly staggering. We're moving out of an era where we just had to accept whatever an AI model hallucinated, and into an era where we can query, audit, and mathematically override an AI's beliefs on the fly. So I want to leave you with this provocative thought to chew on as we enter this completely redefined era of automated governance and AI authorship. If we can now deterministically execute mathematical patches to delete AI knowledge, who ultimately controls the physics of digital truth? Thank you so much for joining me on this explainer, and keep questioning the code.